So next talk coming up is will be industry's sponsored talk by United Imaging, be given by Dr. Ling Zhi Hu from United Imaging. Talk title is Addressing Clinical Challenges in Vascular MRI Using Machine Intelligence. Dr. Hu.
Thank you for the introduction. Sorry being late. I see the agenda. I'm the third talk, so I was preparing outside of the door. Good afternoon, everyone. It's such a great pleasure to be here and share with everyone some of the thoughts and latest technology we have been developing at United Imaging, which hopefully can address some of the clinical challenges you are facing today in your clinical practice of cardiovascular imaging. So what are the major challenges from our understanding in current cardiovascular imaging today? Number one is definitely speed. How we can expand the use of MRA on more patients with more clinical indications. And number two is the resolution. How we can improve the visualization of more details of the blood vessel so we can see more small blood vessels. And more importantly, how we can get more detailed delineation of the blood vessel wall, and so we have more in-depth understanding of the plaque deposition. Third is quantification, how we can streamline the workflow. So today, the technologists and the physicists need to do the post-processing one by one, a lot of manual operation involved in the post-processing. And how we can streamline the workflow so that we can do very consistent quantification of the flow of the plaque and the myocardium. I think the natural solution for all these clinical challenges is the same buzzword. It seems like AI is a solution to all the problems we are facing. And I think AI could be another solution to address the clinical challenge of cardiovascular MRI as well. As the fourth industrial revolution, AI does unleash many of the potential we can do with the MRI in the modern world. However, when we talk about the AI, we have to talk about where we start from the AI. One basic philosophy we have when we develop all United Imaging MRI scanner, as well as many other scanners, is we believe intelligence can only unleash the power, the potential of a machine to its design limit. I think even though we have the latest and greatest medical robots driving an 18th century cargo, this cargo will not go far. Probably it's hard for this cargo to drive from Tokyo to Sendai in a day or two. So with that, I will share with you some of the latest technology we believe may have a potential application in transforming and reshaping clinical MR angiography in a daily basis. And we bundle all this technology into this platform called UI5 platform. The first and foremost technology we believe is a major breakthrough these days is the super flexible coils. These next generation blank-like RF coils allow us to pack much more RF channels into fixed surface area. On top of that, these coils are so much more flexible compared to traditional hybrid, soft and hard shell hybrid coils, which allows much better comfort for the patient, much easier operation from the technology's point of view. Across the imaging platform we have at United Imaging, we have the big body coil with 24 channel, we have the super flexible coil with 12 channel, and we also have a smaller flexible coil with much higher coil density. Hopefully the video will play. Great. So on the top is what does a traditional RF coil look like. Coming from an MR physics background, I was building coil like that myself when I was doing my PhD 15 years ago. It's all copper. Copper is great. Very good conductivity, very low noise. But one biggest challenge of copper is that it's still a metal. It's hard to bend, and it come up with a lot of heating problems, come up with a lot of electronics, the pre-amplification problems. On the bottom, however, is how we build the next generation super flexible coils. As you can see here, we are replacing the copper with this new conductive polymer composite. With all the great advancement in material science, now this polymer composite can carry the electronic current at very high conductivity, very comparable to the copper wire in old days. And with this new material, these new coils become very flexible. You can wrap that around, and you can easily place that around the imaging pods you want to do. And another challenge we didn't mention about here is the pre-amplification of the front-end signal. In MRI, we're detecting 13 protons over 1 million protons due to the Mother Nature Boltzmann distribution. So we need to have very strong pre-amplification. And traditionally, we need to build in the preamps for all the loops inside the coil. And what we have been working on at the first generation of this super flexible coil is to make this preamplification much smaller compared to its old version. And now in the future, our direction is actually to remove all these preamplifiers outside of the coil blanket, so that the coil just a pickup coil, a loop, and all the electronic amplification happen outside of the coil itself. As you can see here, traditional body coil with 12 channels versus a super flexible coil, body coil with 24 channels. The imaging quality and in terms of the details and surface and the signal noise ratio contrast is much better with this latest coil technology. And another technology that I think will reshape the clinical workflow and adoption of MRA is triggering. Trigger is everywhere, and ECG trigger, respiratory trigger. Especially when we do MRA, we're dealing with a lot of motions. We need to have this respiratory bellow. It's a gold standard these days. The technologies need to put the bellow around the patient, and the bellow pick up this respiratory movement of the abdomen and give a respiratory wave which you can use to trigger the acquisition of the MR sequence. It has been taken for granted for the past 20 years. However, there was a major drawback of this way of doing imaging. Number one, many patients, they just came out from operation room. They may have big incision on the abdomen. Adding a belt, adding a bellow on top of these patients can be pretty intimidating. And on the other hand, the bellow sometimes is not sensitive enough. You cannot wrap around too tight, or you cannot wrap around too loose. It's highly operator dependent. With that, in order to achieve consistent respiratory triggering with this UI5 platform, we are the first in the industry to integrate millimeter wave radar into the MR board. It is the same radar technology you would use on a Mercedes-Benz, where the car uses millimeter wave technology to detect the distance between the car and the car in front of them, to measure the distance. However, we follow the same philosophy. We're building the chips in the MR board which send out 60 gigahertz millimeter wave signal to the patient and pick up the rebouncing signal from the patient. With that, we can calculate the sub-millimeter movement of the patient abdomen inside the MR board. And we have two of these radars building at the same time in the MR board. With these two radar, the coverage can be from head to the pelvic of the patient. No matter you are imaging a patient with the head in or feet in first, you always have good coverage of the patient's chest and abdomen. And there are a lot more potential of this millimeter wave radar that we don't have time to dive into details today. As a quick example, here are some clinical validation papers demonstrating very similar imaging quality compared with traditional respiratory wave bellow with millimeter wave radar. And the same technology can be used to trigger almost every single clinical pulse sequence. Here is a typical T2 weighted fast spin echo and MRCP sequence, a 3D MRCP with water imaging technology. On the right-hand side, we can use the same trigger to do a non-contrast MRA to allow very consistent imaging acquisition. And with all these hardware and system foundation, now we can integrate all the AI into the system. We divide the AI from the very beginning of the data acquisition to the image reconstruction to the post-processing. Let's start from the data acquisition. MR has been going faster, has been always the dream of all the MR physicists. We're starting from single echo, then we move on to fast spin echo, EPI, and the most latest technology is compressed sensing. At Unite Imaging, we integrate the AI into the iterative process of all this physics reconstruction of the MR generation and acquisition. Instead of using AI to predict what the final image will look like, we integrate the AI neural network into the iterative process and ask AI to give a prediction of the updating factor in the iterative reconstruction. Here are a quick example showing that compared with compressed sensing, AI-based iterative reconstruction can reduce up to 30% of the scan time, and which will make a dramatic difference in terms of clinical adoption of many non-contrast MRA. Here is an example of imaging pediatric patients. With this AI-based iterative reconstruction and acquisition, we can achieve a 16% or 16 seconds per bed acquisition to show the detailed abnormality of the vasculature. And in cardiac imaging, the same technology has even higher potential because of the temporal information. We can reduce the breath hold of a typical 9 breath hold, 9 slice cine acquisition into 1 breath hold, 9 slice cine acquisition. That dramatically widens the clinical application of this cine image because it's great image compared to echo. It's much more accurate ejection fraction. And with one single breath hold, whole heart from apex to the base, we can calculate accurately of the ejection fraction. And in addition to that, we can also calculate the strain analysis. Last but not least, with all this ACS technology, while we are only need to acquire much fewer number of case-based lines, when we come down to the MR-based coronary artery imaging, it's much faster. Traditionally, because of we need to do real-time navigator gating, we have to reject a lot of arrhythmia. The MR-based coronary artery imaging never took off in the past 10 years. However, we do see a big potential over there with all this ACS undersampling technology. There was a potential for the MR coronary angiography to take off in the next couple of years. Now let's move on to the imaging reconstruction. For the imaging reconstruction, I think we have a great potential. I think all the vendors are working toward the same direction. We want to get the best image quality from the same case-based data. Now we can have a good guess of the case-based data and ask the AI algorithm, CNN network, to give a reasonable guess of what will be a high-resolution version corresponding to this particular case-based data. Then we do inverse Fourier transform to go back to check if this guess is reasonable by comparing the case-based consistency. If the K-space is consistent, that's probably a good guess. That's a basic philosophy of how we do a deep learning, denoising, and super resolution in K-space. And at Unite Imaging, we expand the technology from 2-dimensional to 3-dimensional, which will make a huge difference. As you can see here, here's a typical 3-dimensional T1 fast-spin echo acquisition with FetchSet with 3D ACS and deep learning-based reconstruction. We are reducing scan time by 50%. So it's only less than 3 minutes whole brain resolution, whole brain acquisition with 0.4 millimeter isotropic spatial resolution to image the blood vessel wall. Here's another case. The whole acquisition is still 2 minutes, 55 seconds. With ACS and deep learning reconstruction, it allows high quality isotropic vascular wall imaging for comprehensive evaluation of the blood vessel abnormality. Last but not least, I want to touch base a little bit on the post-processing, because acquisition is one end, and by the end of the day, many times the physician and technologist needs to post-process all this image before we make a final diagnosis, and usually that's very time-consuming. At Unite Imaging, we integrate all the AI-based post-processing into the scanner, into standard non workstation, into our web-based application. Across all the platforms, the AI-based algorithm is exactly the same. You can have immediate access to all these advanced post-processing, no matter what platforms you are using. Here's a quick example. Traditionally, we need to use manual contouring to get rid of all the high background in this non-contrast MRA. Now, with the deep learning neural network, it automatically crop out the blood vessel. That significantly saves the post-processing time. And for the plaque analysis, we can automatically detect the blood vessel. We can automatically use CNN neural network to segment out different sections of the blood vessel. And at the very end, we can use another deep learning neural network to do automatic plaque deposition analysis, which allow a one-stop plaque vulnerability analysis. Here, as you can see, we can input multi-parametric image with and without contrast as an input to this post-processing software. And by the end of the processing, the software will tell the user how vulnerable the plaque is, what is the deposition, what is the risk factor of this particular plaque, and what is the level of the stenosis in this particular segment of the blood vessel. As the first speaker mentioned, blood flow is another key application of that. There was a huge potential to employ deep learning algorithm into 4D flow applications. Here's just a quick example demonstrating how 4D flow in the cardiovascular imaging offers better insights compared to traditional IVUS ultrasound echo, Doppler echo imaging. And in Unite Imaging, this UI5 platform is not only designed for one system. It's across the board, from 1.5T all the way to 3T, all the way to our PET-MR systems. And as a relatively new kid on the board, on the playground, we started to get into the MR market in 2014. But we are growing really fast with the support of the community in global MRI community. We have over 1,500 installations of our 1.5T magnet in almost every continent in the world. We have over 460 3T magnets installed as for today. And it's not mentioning that we also have over 30 3.0 Tesla PET-MR installed in the US, in India, in China, in Middle East. And that number is updating every single day. So with that, I would really love to thank you again for organizing this industrial sponsorship lecture. And I will be there and very looking forward to have more detailed discussion with you all. Thank you so much.
This talk is open for questions.
I'm so sorry.
Go ahead.
Yeah, it's my first SMRA, so I promise I will not make the same mistake next time.
Thank you so much for the impressive pictures. What I, as a radiologist, want to have is a coil where both foot and lower legs can be imaged in a twist sequence. For instance, in Siemens, the other, maybe you have like this and pronounce it another way. But this kind of coil we request over years. What do you think, when will they come?
First of all, we are United Imaging. I cannot speak on behalf of Siemens, but from my technology point of view, I think with all these super flexible coils, there is a potential we can have a large blank-like coil, and your technologist can use that coil to wrap around your patients in a very flexible way. So that way, hopefully, it can cover both the ankle and the feet, and all the way to the lower extremity.
Thank you. And one short comment. The picture you showed us from the child, it's not hemangioma, it's an AV fistula. It's quite different.
Thank you, thank you. Yeah, that's another proof that I'm new to this society. I was doing cardiac MRI, so the cardiac is the only one I know, but next time I will know better.
Any more questions from the floor? I do have a question, Dr. Hu. That milliwave technology for detecting motion is actually quite interesting. I was wondering whether this technique would still work if the patient was covered by a blanket, because that's often the case where patient may feel a little bit cold inside and the technologists use a blanket.
Yeah. Actually, the beauty of the millimeter wave radar compared to camera, if you are reading the news, there was a big debate in the automobile industry as well, because the camera will suffer from the coverage. If the patient have a blanket covering that, if it's a foggy weather, the camera may fail. However, the millimeter wave is only reflected at the surface of water-air interface. And having a blanket covering the patient will not create a surface interface that's strong enough to reflect a millimeter wave. So the millimeter wave basically will go right through the blanket and got bounced off at the surface of the human skin.
Okay, great.
Yeah.
If no more questions, let's thank our speaker again.